All right, let's get started. So the last time we have been discussing about transactions, which is this sequence of updates and queries that are semantically connected. And we have seen a few guarantees that the database system makes when executing those transactions. And one of those guarantees is that we isolate different users from each other, which might be executing transactions concurrently on the same data. And if you are not careful, then this might lead to strange behavior from the user's perspective. So isolation is the guarantee that users will not be aware that multiple transactions are executing concurrently. And the process by which we achieve that is called a concurrency control. Here you see the overview of what concurrency control achieves. The input is a set of transactions, each transaction with a couple of steps. And the output is basically a schedule, which describes in which order the steps of different transactions are executed. Now, that would be pretty simple as long as we execute one transaction after the other one. But for performance reasons, we don't want to do that. We want to interleave the steps of different transactions. And that means that we have to be careful when selecting a schedule. So the goal of concurrency control is to select a schedule which provides isolation, while at the same time being as efficient as possible. And all of this happens at runtime. So concurrency control also needs to be very efficient. So first of all, in the following, we're going to discuss about how we select the schedule that we want to execute. Now the schedule, as I have mentioned, that is ordered steps, where each step is a read or write operation from multiple transactions. And a good schedule will provide isolation, so users don't observe any of those anomalies that we have discussed last time. At the same time, a good schedule is cheap to execute. So we want to select ideally the cheapest schedule among the ones that avoid the relevant anomalies. On the other side, we want to reduce the overhead of concurrency control itself. So that means we might make some kind of compromise. For instance, we might not consider all possible schedules when selecting the one for execution, but only a subset if doing so reduces the overheads of concurrency control. So in the following, we're gonna discuss about a couple of alternative criteria according to which we can select the schedules to execute. What we will finally come to is something like a sufficient goodness criterion for schedules that is quick to verify. So sufficient means that if this criterion is satisfied, the schedule is guaranteed to be good to avoid the anomalies that we want to avoid. On the other side, there might be some good schedules that we are overlooking according to the criterion because it is only a sufficient criterion and not a necessary criterion. So here we make a compromise, but in exchange, we get a criterion that is pretty quick to verify. So the overheads of concurrency control are low. And in the following, we're going to discuss about a few different alternatives. So what is a good schedule? Now, a good schedule generally avoids the anomalies which destroy the illusion of being the only user executing transactions at the same time. So we will define good schedules by comparing to a gold standard, which is essentially a serial schedule. So the user should feel as if transactions are executing serially, meaning one after the other one, while in reality, we interleave the steps of different transactions. But if we compare a candidate schedule to some serial schedule and we find that they are equivalent, then we can conclude that the candidate schedule is also good when it comes to isolation because it looks like one of those serial schedules. So in the following, we're going to see a couple of criteria that allow us to compare different schedules against each other. We will see final state equivalence, where we compare essentially based on the final state that you have in your database after executing the two schedules. Then we compare according to view equivalence, and that means when comparing two schedules, users essentially see exactly the same things in the same order for both of those schedules. And conflict equivalence means that if you have pairs of steps in one of those schedules which conflict with each other, because for instance, both steps, they change the value of the same object in the database, then we essentially have those operations appear in the same order when comparing those two different schedules. So this is an overview. Now we're going to discuss those criteria in more detail. Starting with final state equivalence. So here we say that two schedules are equivalent if the final state of your database is the same after executing them, starting from an arbitrary starting state. All right. So for instance, if you look at those two example schedules here, and I'm going to seize the opportunity to quickly remind you of the short notation for schedules that we have introduced last time. So here you have those W's, which always means a write operation. So we change the value of an object in the database. Then you have those R's. Actually, here you don't have R's, but in general, for the schedules that we will see on the next slides, you have R's. And in that case, it's a read operation where we read the value of an object in the database. With this notation, you always have, for instance, the type of operation, which here is a write operations, W, followed by the ID of the transaction executing that step. So we always use numbers for transactions. So here we are starting with a write operation by transaction 1. And then between parentheses, you always have the object in the database that the write operation refers to. So here we have object A generically. And in reality, concretely, that could, for instance, correspond to one row in your database. For instance, initially we had an example where we transferred money from the account of Alice to the account of Bob. Then you have to change values for those two database transactions. Okay, and here we have the question whether one query ever can have multiple transactions. So just to make sure, queries are included as part of a transaction. So basically, one query would be a part of a transaction and update operations as well. All right. You also have the C's here in this example schedule. A C always means a commit operation, and after the C, you have the number of the transaction committing. So if a transaction commits, it always means that the transaction essentially is finished and wants to get executed. All right. Now here, when comparing those two example schedules, in the first schedule, transaction 1 executes first and writes values to A. And okay, so here actually in the first schedule, we have first a write operation by transaction 1 to object A. Then we have a write operation by transaction 2 to object A. So the final value for A will be written by transaction number 2. Then we have a write operation by transaction 1 to object B, followed by a write by transaction 2 to object B. So also for B, the final value will be written by transaction 2. And finally, both of those transactions commit. Now, the second schedule over here first writes a value for object A via transaction 1. Then transaction 1 writes also the value for B and commits. After that, transaction 2 writes the value for A and the value for B. So when comparing those schedules, then in both of them, transaction number 2 writes the final values for objects A and B. And that is why those two schedules are final state equivalent. If we say that a schedule is final state serializable, it means that there is some serial schedule which contains the same transactions that is a final state equivalent to that schedule that we are analyzing. And this other schedule that we are comparing against must be a serial schedule executing transactions one after the other one. So a schedule is final state serializable if we can find a final state equivalent serial schedule. Now, final state equivalence can be efficiently verified, which is good. But on the other side, it is not sufficiently strong as a criterion in order to avoid all those strange anomalies that we have discussed in the previous lecture. For instance, we have heard about this anomaly unrepeatable reads, where I read one value once, and then later I read it a second time, and the value has been changed in the meantime by another transaction. So that is bad. And even if a schedule is final state serializable, it could still have those unrepeatable read anomalies. So for instance, if you look at the schedule over here, we have first a read by transaction 1 of object A, then a write by transaction 2 to object A, and finally another read by a transaction 1 of object A. So here you have an unrepeatable read because the second transaction might have changed the value of A in the meantime. On the other side, the schedule is final state serializable because transaction number 2 writes the final value for A in any case. All right, so probably we want a stronger criterion than final state serializability. That leads to a view equivalence, and there we compare two schedules based on what the user sees in which order. And we have a whole bunch of conditions such that two schedules S1 and S2 are view equivalent. First of all, if some transaction reads the initial value before schedule execution starts of some object in one schedule, then it must also do so in the other schedule. Also, if a transaction reads the value of an object that was written by another transaction before, then it must also do so in the other schedule. And then finally, if some transaction writes the final value of an object in the first schedule, it must also do so in the second schedule. So we require all three conditions in order to say that those two schedules are view equivalent. Now you see here, we have some conditions that relate to the final state of the database, because if the final value was written by a transaction in one schedule, it must also have been written by that transaction in the other schedule. But we additionally have some conditions which refer to what the user sees or what the transaction sees. If a transaction has seen the initial value in one schedule, it must also see it in the other schedule. And if a transaction has seen the value written by another transaction in the first schedule, then it must also do so in the second one. And that is where the name view serializable comes from. And here, all right. And there's a question in the chat that refers to a little typo here. So the last point actually should be that if a transaction X writes the final value in S1, it also does so in S2. Yeah, so that is a little typo. Thank you. All right, so here the last condition basically means that the final value of those objects should not change when comparing the two schedules. So that is basically referring back to final state serializability. All right. And then view serializability again means that we find a serial schedule which is view equivalent to the schedule that we are analyzing. So for instance, here's an example where we are trying to determine whether a specific schedule is a view serializable. You see the schedule that we are analyzing here. First, we are reading the value of object A by transaction 1. Then we are writing, then transaction 2 writes the value for object A. And then transaction 1 reads the value for A again. So this is the schedule that we have already seen before. And here we have potentially an unrepeatable read. So we expect that this schedule is not view serializable, but let's make sure. So since we have two transactions that appear in this schedule, there's exactly two possible serial schedules that we can compare against. Either we first execute the first transaction and then the second transaction, or we first execute the second transaction and then the first transaction. Now, here we have both possibilities. So either we could have the first transaction execute first, then followed by the second transaction. But this schedule, the serial schedule, is not view equivalent to the schedule that we are analyzing, because the second read of object A, in one schedule, it reads the value written by the second transaction. In the other schedule, it reads the initial value. So that violates one of the three conditions. In the other case, where we execute the second transaction first, we have that both reads of A by the first transaction, they read the value written by the second transaction, but none of them reads the initial value. And in the schedule that we are comparing against, one of those two read operations reads the initial value of object A. And because we cannot find any serial schedule that is view equivalent with the schedule that we are analyzing, therefore, this schedule is not view serializable. View serializability seems like a nice criterion. It is pretty strong, so it avoids those anomalies that we have seen. The only problem with that criterion is that it is NP hard in general to verify whether a schedule is view serializable. And NP hard generally means that we don't know and don't believe that there exist any efficient algorithms in order to solve that problem. And selecting a schedule that is something that the concurrency control component needs to do at runtime very quickly once transactions are being submitted. So we most definitely don't want to solve any NP-hard problems at runtime, because that would slow down the entire database system. So this is an overview of what we have seen so far. This is an illustration of the different classes of schedules that we have been discussing about, as well as how those different classes of schedules relate to each other. You see that we have inclusions among them. We have, first of all, the set of all possible schedules which contain the same transactions. Then you have the subset of schedules that are final state serializable. Then you have the even smaller subset of schedules that are view serializable. And finally, you have the small set of schedules that are indeed serial. So all of those inclusions are proper, so you can always find the schedules that are included in the larger class, but not in the smaller class. Now, having discussed all of those different classes of schedules, our final goal is to select a class of schedules that we want to aim for in concurrency control. Now, serial schedules are easy to verify, but they are very slow to execute. We have seen a couple of motivations for why we want to avoid serial schedules that execute one transactions after the other one last time. We have seen view serializable schedules, but the problem with them is that they make concurrency control very slow because we would have to solve NP-hard problems. We have seen final state serializable schedules, but here the problem is that we might have anomalies. So we destroy the illusion of isolation. And then we have the set of all schedules, and there we have exactly the same problem. So in a way, none of those classes of schedules seems to be a good choice for aiming as a goal in concurrency control. So we need something else. And in the following, we're going to discuss an alternative class of schedules that is a much better compromise between those different quality criteria. All right. Now, the class of schedules that we will be aiming for is a conflict serializable schedules. And so first of all, we introduce a conflict equivalence and say that two schedules are conflict equivalent if they have the same conflicts appearing in them. Now, what is a conflict? So a conflict arises between two steps of like two different transactions if they operate on the same object, and one of those operations is a write operation. That is important because as long as transactions are just reading data, everything is fine and nothing bad can happen. But as soon as transactions start changing the data, this is where we need to be careful that we don't interleave transactions in a bad manner. So for a conflict, we must have two operations by different transactions, where one of those operations is a write operation. And that leaves essentially three possibilities. We could either have first a read by the first transaction, followed by a write on the same object by the second transaction. Or we could have first a write by the first transaction, followed by a read of the same object by the second transaction. Or we could have two writes by two different transactions on the same object. Those are the possibilities. Whenever I change the order of some of those conflicting operations, so I change the order in the schedule, whenever I do that, I have a risk of creating differences, either in terms of the final state of the database or in terms of what the users see in which order. On the other side, as long as I only change the ordering between non-conflicting operations, I cannot have any of those bad effects. The final state will be the same, and also users will see the same things in the same order. So I can say that two schedules are conflict equivalent if I get from one schedule to the other one by only swapping non-conflicting operations. And in line with that, we have conflict serializability. A schedule is said to be conflict serializable if there is a serial schedule, and I can make sure that the serial schedule is conflict equivalent to the schedule that I am analyzing. Now, for a given set of transactions, of course, there's many different serial schedules. So I don't want to try out all of them and compare them in terms of conflict serializability, in conflict equivalence. Instead, I want a more efficient method to test whether a given schedule is conflict serializable. And we can do that by the method that I'm going to describe in the following. It involves drawing a so-called conflict graph. We will see in a second how to define that conflict graph for a given schedule. But it comes in the end down to testing whether this conflict graph has a cycle, and the schedule is only conflict serializable if this graph has no schedule, and that is something, it has no cycle, and that is something that we can test very efficiently. All right, so this is the definition of the conflict graph. So if we want to find out whether one schedule is conflict serializable, then we are drawing this conflict graph for it. And in the conflict graph, we are introducing one node for each of those transactions in the schedule. And then for each pair of conflicting operations by two different transactions, operation O1 and operation O2, we draw an edge from the transaction to which O1 belongs to the transaction to which O2 belongs. So this edge in the conflict graph basically indicates a conflicting operation between those two transactions. We draw that edge from the earlier transaction, from the transaction with the earlier operation, to the transaction with the later operation. Let's make a little example. So here we have a schedule given on top in purple. It involves 3 transactions. So definitely the conflict graph must have 3 nodes. Now, can anyone tell me which conflict edges I should draw in my conflict graph over here? Or at least, can anyone identify, for instance, one pair of conflicting operations and tell me what edge I need to draw in the conflict graph because of it? In the chat, please. Okay, there's a couple of things coming in. Okay, good. So in general, 2 operations conflict if they belong to different transactions. They operate on the same object, and at least one of those operations is a write operation. So here, for instance, we have the proposition R1 of C followed by W3 of C. So let's see here. R1 of C, we have it here. And then W3 of C, we have that at the very end, exactly. So here we have the same object, we have different transactions, and one of them is a write operation. And that means that we want to draw a line from the first transaction to the third transaction. All right. W2B and W3B. All right. Okay. Exactly. So here we have 2 conflicting operations following each other immediately. One write to B by transaction 2 and one write to B by transaction 3. Transaction 2 goes first, so we want an edge from transaction 2 to transaction 3. Now we have another one, W1A to R2A. All right, where do we have W1A? Okay. So R2A goes first, right? So we first have the read of A by transaction 2, and later we have the write to A by transaction 1. So we would want to draw a line from 2 to 1. Okay, very good. So this is the principle. Compare pairs of operations in the schedule and see whether they conflict, and then draw the corresponding edges in the conflict graph. So we have collected all of them. Here now I'm drawing the edges. I believe we covered all of them. Very good. All right, so that is the conflict graph. And finally, I would have to check whether that conflict graph has a cycle or not. And in this case, we don't have a cycle. So this one is a conflict serializable. All right. So perhaps to illustrate that point a little bit more, why is it that we are looking for cycles? So if you have an edge from some node I to a node J representing 2 different transactions, then essentially means that any conflict equivalent serial schedule must order transaction I before transaction J in order to avoid swapping the order of those conflicting operations. And because of that semantics, the way in which I can transform one schedule that is conflict serializable into the conflict equivalent serial schedule, it's by essentially doing a topological sort in the conflict graph. So essentially I start, first of all, with the transaction whose node has no incoming edges. Then I take all the operations of the transaction and write them into my new conflict equivalent serial schedule. Then I continue finding one node where all incoming edges belong to transactions that have already been treated. And I continue doing this until finally I know that I have treated all the transactions in the current schedule. For instance, in this example over here, we would first start with a transaction 2 because node 2 has no incoming edges. So I can order the operations of that transaction first. Now, node 1 next doesn't have any incoming edges from nodes that haven't been treated yet. So I'm gonna put transaction 1 next. And now finally, I can put the operations of transaction 3. And now I have a serial schedule that is conflict equivalent to the original schedule, and can do that quite easily using the conflict graph. All right, so this is where we stand now. We have found one new class of schedules that are conflict serializable. There's one little drawback to them. They are a little bit too restrictive, meaning there's some good view serializable schedules that don't create anomalies, but they would not be allowed according to the conflict serializability criterion. But what we get in exchange is a criterion that is very efficient to verify using this conflict graph that we have seen. And that is why we will be aiming for creating conflict serializable schedules via concurrency control in the following. It is a compromise between different criteria. All right, good. Any questions on this at this point? All right, and otherwise just put them into the chat. All right. So far we have been classifying schedules into this hierarchy, but we haven't really talked about aborts yet. So when testing, for instance, whether a schedule is conflict serializable, you would first of all take out the operations by all transactions that are finally aborting, because the database management system essentially guarantees that transactions that have been aborted, that everything looks like they never happened in the end. So when testing all those previous criteria, we are not at all considering transactions that have been aborted. On the other side, aborting transactions is something that is actually quite common in practice. So we also want to take it into account when choosing a schedule. So in the following, we're going to see another classification of schedules, which is orthogonal to the previous one, and it deals primarily with transaction aborts. And here there's a question, I think, that still refers to the conflict graph. If we have a cycle, is it considered as a programmer's fault, or will it be randomly selected when one starts executing? If there's a cycle in the conflict graph, it means that the selected schedule is not conflict serializable. So typically, the concurrency control component would aim to select only schedules that are conflict serializable. So if there's really a cycle in the conflict graph, that is something that should not happen when you use a concurrency control method that aims for conflict serializable schedules. So the goal of concurrency control is to avoid any cycles in the conflict graph and to select schedules which don't have them. So yeah, if that happens, would be the fault of the programmer of the database management system. Okay. All right. So first of all, we will discuss about recoverable schedules. Recoverable schedules, it's a very basic criterion saying basically that your schedule should leave the database in a consistent state. It's a very basic requirement. If you look, for instance, at the schedule marked in red over here. So what we're doing here is we first have a write to object A by transaction 1, followed by a read of object A by transaction 2, and a write by transaction 2 on object B. And now transaction 2 commits, but a bit after that, transaction 1 aborts. And that creates a huge problem for the database system, because the database wants to guarantee that committed transactions are never undone. On the other side, it wants to guarantee that aborted transactions have no effect whatsoever on your database. And the problem is this. Transaction number 2 has read the value of object A that was written by the first transaction, which means that transaction 2 might have been influenced in what it writes to object B by what it has read from object A. And that means that logically, if transaction 1 had never happened, then transaction 2 might have written a different value to object B. Now, that creates a problem. On the one side, we want to guarantee that transaction 2 will never be undone, but it was influenced by transaction 1, and we want to guarantee that transaction 1 has no effect whatsoever on our database state. So this is a situation you totally want to avoid, because here the database system essentially tries to guarantee two things that conflict with each other. We call such schedules non-recoverable. And essentially, in order to avoid such bad schedules, what we need to do is that we delay the commit of a transaction until we can be sure that all other transactions it has been influenced by have also committed. So essentially, we want to make sure that a transaction only commits after all the transactions it has read from have committed. And if I have that, then I have a recoverable schedule. Now, recoverable schedules, that is something that you want in any case, but aborts can even create problems if a schedule is recoverable. For instance, if you look at the schedule here below, here we have again, it is, and maybe I should compare to the previous one. So here we have again a write to object A by transaction 1, and then a read of A by transaction 2, followed by a write by a transaction 2 to object B. Now, what we have done here is that we wait with the commit of transaction 2 until transaction 1, which has influenced transaction 2, has also committed. So if you compare that to the previous schedule, here the problem is that transaction 2 already committed before it knew that transaction 1 commits 2, right? So here we have essentially delayed the commit by a transaction 2 until we can be sure that transaction 1 commits as well. That makes it recoverable, which is good. But on the other side, if at this point transaction number 1 decided to abort, then we would also have to abort transaction 2 because it has been tainted by reading a value of object A that has been written by transaction 1. So that means that we have essentially cascading aborts because one transaction aborts and that causes another transaction which has read from it to also abort. That is something that we want to avoid for performance reasons, because if we have like a long chain of transactions where the first one aborts and that causes all the other ones to abort too, that creates huge overheads to the database system. So that's why we're interested in creating schedules that avoid cascading aborts, also called ACA schedules. And in order to get there, the only thing we have to make sure of is that a transaction does not read uncommitted data. If we read uncommitted data, we might have a cascading abort. If we don't read uncommitted data, we avoid that possibility. So avoiding cascading aborts is good. There's still a couple of issues that can arise in the case of aborts if multiple transactions have written to the same object. So first of all, if multiple uncommitted transactions have written to the same object, it means that I need to keep track of which transaction has written which value, because if some subset of those transactions abort, I need to know which is the right value to assign to that object. Also, when, for instance, aborting one transaction and undoing values for an object, reverting them back to the original value, I need to verify whether the current value of the object is actually invalid and whether I really need to undo it. So generally, having multiple transactions write to the same object where all those transactions have not yet committed, that can create some complications in the cleanup. And that is why people in practice often try to avoid such schedules and go for strict schedules instead. Strict schedules generally means that no transactions reads or overwrites uncommitted data. So once one transaction has written a value to an object, then this value will not be read and it will not be overwritten until that transaction which has written the last value has committed. All right. So for instance, here at the bottom of the slide, you have another example schedule where 3 transactions write to object A. Now, this schedule, first of all, is recoverable. We actually don't see any commits at all in this schedule. It avoids cascading aborts because we don't see any reads of uncommitted data here in the schedule, but it is not strict because different transactions override each other's values before any of them commits. All right. So altogether, we have now seen another hierarchy of schedules. We have the set of all schedules. A subset of that is the recoverable schedules. Then we have the ACA schedules that avoid cascading aborts. And finally, we have the strict schedules. So in summary, now we have seen 2 ways of classifying schedules. First of all, based on serializability. There we have seen final state serializable, conflict serializable, and view serializable. And then we have classified them based on aborting behavior. And there we have seen recoverable schedules, schedules that avoid cascading aborts, and strict schedules. And which of those schedules you're going for, it depends on many factors. For serializability in the following, we will be aiming for conflict serializable schedules because it's a good compromise between the quality of the schedules and the overheads of concurrency control. For abort behavior, we will definitely go for recoverable schedules, but then depending on the variant of concurrency control that we are discussing, we might sometimes consider only recoverable schedules, sometimes ACA schedules, and sometimes strict schedules, whatever provides the best performance in certain circumstances. All right, so now we have seen a few classes of schedules, but so far we haven't really seen mechanisms by which we can guarantee one of those schedules we are aiming for. Let me quickly change my slide deck, and if anyone has questions, please feel free to ask them in the chat. And those two hierarchies of schedules that I have shown to you, they are orthogonal to each other. So that means you cannot directly infer anything in one categorization from properties of the schedule in the other categorization. So you can, for instance, not conclude that a certain schedule is strict if it has certain serializability properties. It's two different ways of classifying the schedules. All right, good. So you should now see my slides about two-phase locking. So we have time for a little intro, and then we're going to discuss more details in the following. So we will start now to discuss about mechanisms for concurrency control, and one of the most popular mechanisms, that is two-phase locking. Here we are discussing about the transaction manager component of the database system, the relevant chapter in Ramakrishnan and Gerke, that is chapter number 19. So generally, what we are discussing about now is the algorithms that run inside of that concurrency control component. So what we have seen in the previous slide deck was generally a classification of schedules. So we have seen that we probably want to aim for conflict serializable schedules. We want recoverable schedules, and depending on the situation, sometimes we want ACA schedules, and sometimes we want strict schedules. So now we're going to discuss about protocols which generate those schedules. There's always trade-offs. Ideally, we want a mechanism that allows many possible schedules to consider, because then we can select the most efficient one for execution. On the other side, we want a mechanism that is very cheap to execute. So we might be willing to accept considering less schedules if in exchange it reduces the cost of concurrency control. So in the next lecture, mainly we will be discussing about a locking-based concurrency control methods. Now, we're going to discuss more detail in the next lecture, but already tell you a few basics. So generally, those concurrency control mechanisms will be based on locks, which essentially represent a permission to operate on a specific object. And the mechanisms that we will see essentially force transactions to first acquire a lock on an object before they can work with it. They submit those lock requests to the lock manager, and then they wait until the lock request is granted. And only then do they proceed. The lock manager generally keeps track of which locks has been assigned to which transactions, and it also keeps track of which transaction is interested in what lock, and it queues them, and then it grants transactions with locks and makes sure that no two transactions have conflicting locks on the same object in the database. That is the high-level principle. In the next lecture, we are going to discuss more details for one very popular concurrency control mechanism. Have a nice day, and then I see you on Friday.